Hello everybody, it's Tarun. Welcome to your 15th tutorial in the Signal System and Control course. In the last tutorial, I taught you the discrete time Fourier transform for aperiodic signals. In this tutorial, I will teach you the Fourier transform for periodic signals and some properties of the discrete time Fourier transform. Okay, so now let's start with the Fourier transform for periodic signals. We all know that periodic signals do not meet the convergence condition, okay, but they have discrete time Fourier transform or continuous time Fourier transform if we are taking periodic continuous time signals, okay, and these are constructed with the help of their Fourier series representations. So I am going to teach you with the Fourier transform for periodic signals with some examples. Okay, now let's consider xn is our signal which is having a Fourier transform x of e to the power j omega, which is equals to summation L equals to minus infinite to infinite 2 pi delta omega minus omega naught minus 2 pi L. Okay, as you can see here that x of e to the power j omega, it is a impulse train, okay, because it is the summation of scalar multiplication of 2 pi with delta, okay, which is where delta is the unit impulse function. And if I find out the inverse Fourier transform for this signal, okay, which will be x of n equals to 1 upon 2 pi integration over time period 2 pi summation term, which is the value of x of e to the power j omega, okay, and multiplied with e to the power j omega n t omega, it will give me the result e to the power j omega naught n. So which is a periodic function in discrete time case, okay. So reciprocally or vice versa, you can see that e to the power j omega naught n have Fourier transform summation L equals to minus infinite to infinite 2 pi delta omega minus omega naught minus 2 pi L. Okay, so you all know that e to the power j omega naught n can be written as cos omega naught n plus j sin omega naught n with the help of Euler's formula. Okay, so earlier I was telling you about the two types of Fourier transform for the periodic signals, one for sine and cos and the other is for rest. Okay, here you can see that this term, it is for sine and cos. Okay, so now let's check it with the help of Fourier series representation or derive the general formula. Okay, we are considering x of n as a periodic signal in the discrete time case, which is summation k equals to time period n, okay, or k ranging from k ranging over the time period n, okay, ak e to the power j k 2 pi by capital N into small n, and its Fourier series representation is ak. Okay, so if I take the Fourier transform for this function, then it will be x of e to the power j omega, which is equals to summation k equals to n, k ranging over period n, ak summation L equals to minus infinite to infinite 2 pi delta omega minus 2 pi k by n minus 2 pi L. Okay, so which can further be represented as 2 pi ak delta omega minus 2 pi k by capital N. Okay, so we have deduced it for the general formula. So this is the graphical representation for the different values of k, okay, and for different values of k, the Fourier series coefficients ak will also vary. So as you can see here that the graph value changes, okay, the p value of each impulse changes. Okay, so what is the Fourier transform of any periodic signals? It is a train of impulses occurring at multiples of the fundamental frequency 2 pi by capital N. Okay, this is because we are taking the frequency omega minus 2 pi k by n, where k is an integer. Okay, and the area of impulse at k 2 pi by n is 2 pi times the kth Fourier series coefficient. Okay, so these are the two observations for the Fourier transform for periodic signal. Now let's see some more examples. The first one is sine function. Okay, for the sine function can be represented as 1 upon 2j e to the power j omega naught n minus e to the power minus j omega naught n, as you all know. Okay, and it is periodic if omega naught is 2 pi m by n. So for Fourier transform, what will be the Fourier transform for the sine function? It will be taken by the first formula which I have told you, which consists of omega minus omega naught minus 2 pi l. Okay, and keep in mind that for the sine and cos function we'll use that formula, and for other functions we'll use the omega minus 2 pi k by n formula. Okay, so the Fourier transform will be minus j pi summation L equals to minus infinite to infinite delta omega minus omega naught minus 2 pi l. Okay, and plus j pi summation L equals to minus infinite to infinite delta omega plus omega naught minus 2 pi l. So this is because the Fourier series coefficient of sine function are 1 upon 2j and minus 1 upon 2j. So this one is for minus 1 upon 2j for L for minus 1. Okay, and this is for 1 upon 2j where the value is taken as 1. Okay, this is the graphical representation for the above function. Okay, so similarly you can do the same for the cosine function. Just the difference is that there is a difference of j here. Okay, here earlier it was minus j and j here in case of the sine function. Okay, minus j here and plus j here. Okay, and the other difference is that in case of the sine Fourier transform, the impulse contains both the positive and negative quantities, but in case of cosine function it consists of only positive quantities. Okay, so the third example which I am going to teach you is the impulse train sequence. Okay, the impulse train sequence is xn, where xn equals to summation k equals to minus infinite to infinite delta n minus k capital N. Okay, the Fourier series coefficients you can find out. Okay, which will be 1 upon n. You can solve it. So the Fourier transform will be summation L equals to minus infinite or k equals to minus infinite to infinite 2 pi ak delta omega minus 2 pi k by n. Okay, so ak is 1 upon n, so I can take out 2 pi by n outside, and it will remain, the expression will remain as 2 pi by n summation k equals to minus infinite to infinite delta omega minus 2 pi k by n. Okay, so this was the plot for the original signal, and it is the plot for the Fourier transform signal. So now let's see the properties of discrete time Fourier transform. Okay, there are many properties in the discrete time Fourier transform. Okay, so and some of them are very important, okay, and I'll teach you some of them in this tutorial, and the rest I'll continue in the next. Okay, so now let's get started with the first property, which is periodicity. Okay, the discrete time Fourier transform is always periodic in the omega with period 2 pi. It means that in the expression of the notation of Fourier transform, which is x of e to the power j omega, if I write it as x of e to the power j omega plus 2 pi, then it will remain only x of e to the power j omega. Okay, this is different from the continuous time Fourier transform, because there was no such property in the continuous time Fourier transform. Okay, the second property is the linearity property, which is the same as there was in the Fourier series representation or the continuous time Fourier transform. Okay, so if we are having signal axn plus byn, and its Fourier transform will be a Fourier transform of xn plus b Fourier transform of yn. Okay, which is also applicable in the case of inverse Fourier transform, as you can see here, that if we are taking the whole expression c x of e to the power j omega plus y e to the power dy e to the power j omega and its inverse Fourier transform, then it will be c inverse Fourier transform x of e to the power j omega plus d Fourier inverse y of e to the power j omega. The next property is the time shifting property. Okay, it is also similar as I told you in the Fourier series representation and the continuous time Fourier transform. If x of n is having Fourier transform as x of e to the power j omega, Then x of n minus n naught will have Fourier transform e to the power minus j omega n naught x of e to the power j omega. This time I am not going to teach you the proof because I have told you earlier also. So this time you have to do it yourselves. Okay. The next property is the frequency shifting property. Okay. If we are having x of n as the signal and its Fourier transform is x of e to the power j omega, then e to the power j omega naught n, if multiplied with xn, then it will give us the Fourier transform shifted in frequency domain. As you can see here that x of e to the power j omega minus omega naught. Okay, here we multiplied the complex exponential with omega naught n as its frequency, then our Fourier transform gets frequency shifted by the term omega naught. Okay, shifted means delayed. Okay, if the value of omega naught, or here it was e to the power minus j omega naught n, then it will be advanced. Okay, here it will become plus. Okay, so here is the proof. Now let's take the Fourier inverse for this function, okay, which will be 1 upon 2 pi integral over the time period 2 pi x of e to the power minus e to the power j omega minus omega naught e to the power j omega n d omega. I have replaced omega minus omega naught with omega dash. Okay, as you can see here that it will be e to the power j omega dash e to the power j omega dash plus omega naught into n and d omega dash. Here I can take out e to the power j omega naught n outside. Okay, and now I can replace omega dash with omega again, so which will give me the inverse Fourier for xn. Okay, so it will be e to the power j omega naught n xn. So if I combine the two properties, which is the periodicity property and the frequency shifting property, then it gives us a special relationship between the ideal low pass and ideal high pass discrete time filters. Okay, so now let's see that with example. Okay, we are having a low pass filter which is having cutoff frequency omega c. Okay, and its frequency response is HLP e to the power j omega. Okay, and it's here it is the graphical representation of this. Okay, don't get confused because here you are seeing that it is periodic, because I already told you that the filters are periodic in the discrete time case. Okay, and are for one block only for the continuous time case. And we are having high pass filter with cutoff frequency pi minus omega c, and its frequency response is h of hp e to the power j omega, and its graphical representation is also done there. So the relation between them is that the frequency response relation is there, okay, which is in frequency domain. So h of hp of e to the power j omega is equals to h of lp e to the power j omega minus pi. Okay, and the impulse response will contain the following relation. As you can see here, if you take the Fourier inverse for this equation, okay, if you take the Fourier inverse for this equation, it will be hp of n equals to, by the frequency shifting property, okay, you can see that it will be e to the power j pi n, okay, into h lp of n, which you can, the value of e to the power j pi n is minus 1 to the whole power n. Okay, so this was the relation between the high pass and low pass filter in the discrete time domain. The next property which I am going to teach you is the time reversal property. In the time reversal property, I replace the independent variable n of our original signal with minus n. Okay, we are having xn and its Fourier transform is x of e to the power j omega. Okay, then the Fourier transform of x of minus n will be x of e to the power minus j omega. Okay, for proof, now let's see that we are having y of e to the power j omega, which is summation n equals to minus infinite to infinite y of n e to the power minus j omega n, which is equals to summation n equals to minus infinite to infinite x of minus n e to the power minus j omega n. Here we are taking x of minus n as y of n. Okay, now I have replaced minus n with m, so it will be summation m equals to minus infinite to infinite x of m e to the power j omega n. Okay, so I can again rewrite it in this manner. Summation will remain same, x of m will remain same. Okay, I can write the complex exponential as e to the power minus j into minus omega m. Okay, so which will be e to the power minus j omega. Okay, so the next property which I am going to teach you is the conjugation and conjugate symmetry property. We are having a signal x of n and its Fourier transform is x of e to the power j omega. Okay, if I take the conjugate of our original signal which was x of n, okay, now it becomes x star n. The Fourier transform will be x star e to the power minus j omega. Okay, if our signal x of n is real, then it is called conjugate symmetry. Okay, which implies that x of e to the power j omega will be equals to x of e to the power minus j omega's conjugate. Okay, which is the this relation. Okay, so this is again that summary table which was there in the continuous time case and the Fourier series representation also, that for even real even part of x of n, the Fourier transform will be real even part of x of e to the power j omega, and for each imaginary even part of x of n, it will be imaginary even part of x of e to the power j omega, and for real odd part, it will be imaginary odd part of x of e to the power j omega, and for imaginary odd part of x of n, it will be imaginary even part of real odd part of x of e to the power j omega. Okay, so now let's see one example. We are considering x of n which is equals to a to the power mod n, where mod a is less than 1. Okay, I have considered x of n as z of n plus z of minus n minus delta of n. Okay, where z of n is a to the power n un. Okay, so this is because I can rewrite this equation in this manner, and this is so because if for the z of n, it will be a to the power n un, which shows us that it is an unit step function having value a to the power n as n tends from 0 to infinity, and for z of minus n, it will be a to the power minus n. Okay, which u of minus n, which will go from 0 to minus infinite. So as you can see here, that at 0 it will get added 2 times. Okay, which will be a of 0, a to the power 0 plus a to the power 0. So I have subtracted delta n from this once to get rid of the extra term which I have added, and we all know that the Fourier transform for this z of n function is 1 upon 1 minus a e to the power minus j omega. Okay, and with the time reversal property, the Fourier transform for this z of n function, z of minus n, will be 1 upon 1 minus a e to the power j omega. And we all know that the Fourier transform for delta n is 1. Okay, so finally the x of the Fourier transform of x of n will be x of e to the power j omega, which is equals to 1 upon 1 minus a e to the power minus j omega plus 1 upon 1 minus a e to the power j omega minus 1. Okay, by simplifying this equation, you can get this expression. Okay, so if x of n is real and even, then x of e to the power j omega is also real and even. Okay, so this was all from my side in this tutorial. In the next tutorial, I'll start with the property first order differencing. So thank you guys for watching. I'll see you in the next tutorial.